third presentation, the third and last presentation of this meeting. It's going to cover a testbed of the IIC, which is called the Microgrid testbed. Our speaker is Dr. Gerardo Pardo Castellote, who is the Chief Technology Officer, CTO at Real-Time Innovation, RTI, which is one of the companies that implements the data distribution service, which is an OMG standard. Gerardo has been their RTI, the company I just mentioned, for 23 years. No, it says 95. That's 23 years, my God. You know,
wow.
You started when you were 2 years old.
That's right.
To repeat the Richard Soli's favorite joke. He specializes in real-time software architectures and networking. He's worked on time-critical software for data acquisition and processing, real-time planning and scheduling, control system software, and software system design. He is the author of the original version of the data distribution service, the version that RTI offers. He chairs the data distribution service finalization task force at the object management group. And DDS is not just one standard, it's a family of standards. So that keeps him busy because every time they finish one addition to DDS, they start on the next one. He has a doctorate in electrical engineering, a master's in computer science, and an MSc from Stanford University, so he has to be a good person because I'm a Stanford guy too. And before that he got his BS in physics from the University of Granada in Spain. So,
thank you. So, it was a great presentation. And I think this is kind of is great sort of complementary, because I think it's addressing a lot of the same issues, and there's a lot of similarities in the approaches, and maybe a few interesting differences that we can then discuss and have a good discussion. But I think so I'm fundamentally going to be talking about the microgrid testbed of the IIC, but I'm going to motivate a little bit of why we're doing this and how we're approaching it, and then what technologies and what standards we're using to implement this testbed. And I think the motivation is very similar to your presentation. It's basically we're going from the current situation, well, maybe it's not current anymore, like I already have solar, a lot of people have solar, but what is considered to be, I guess, what's been the norm for a long time, which is centralized energy generation, to a more increasingly distributed generation of energy and resources. And that has, as we've seen in the presentation before, it has a lot of challenges, and it also brings a lot of new opportunities, right? We can make things a lot more resilient, a lot more reliable, the economics can be a lot better, but right now there are challenges because the technology wasn't developed with this kind of use case in mind, and therefore there's a lot of inefficiencies. So, and great discussion about the aspects of energy trading and all these things, so that falls into the aspect of the opportunities. Now we are sort of, for my background and for the IIC testbed, we're kind of focusing more on the challenges. So we're not as ambitious as your effort that's trying to kind of address the whole problem. We're kind of sitting more down there saying, let's enable the fundamental technical blocks that are required to then have this smart application to go on top and solve the problem. So what is this challenge from the point of view we're seeing? Is where we see that a key component of the distributed energy resource is this concept of islanding and microgrids, right? And you mentioned when the power was kind of turned off and you have this section of the grid that now can function autonomously. That's kind of the idea of a microgrid, where you have both generation of power and use of power locally in some area, and now you kind of manage that as a separate unit from the rest of the grid, which can be integrated, so you can exchange power, but also you can function autonomously, right? So you have a lot of efficiencies and benefits from that. I mean, you have the benefit, obviously, that if there's some power in the broader grid, then you can essentially still functioning. But I think, from the physics aspect, if the energy doesn't travel so far, right, you get also a lot less need for, there's a lot of less loss in the sort of energy distribution and so forth. So, so microgrids are an important component now. one of the key difficulties with energy, electric energy specifically, is that it's very hard to store, right? And if you've got generation and you've got consumption, but you don't balance the generation with the consumption, then that difference has to go somewhere, right? And in some cases, well, how do you store electric energy, right? So, well, you have batteries, but batteries are quite expensive. And you have other mechanisms, but that sort of presents a challenge, and in fact, it's one of the inefficiencies that we're seeing today is that a lot of the sort of storage mechanisms that are out there are essentially like what they call like rotary type of storage, where it's storing kinetic energy or something like that. So ideally, what you would want to do is essentially have a way to balance the generation with the consumption, so you don't have to put a lot of emphasis on storing the energy, or in what could even be worse, wasting the energy. In some cases in which you just kind of burn off the energy that you can't balance, right? So, this is the challenge now. There's a lot of things that are going in sort of in the right direction, right? Because people are using more electric sort of solar power and batteries, and then electric vehicles and so forth. So all this is kind of like moving in the direction of storing energy. And then you can also imagine that if you have a more integrated system, there are some energy sources that you can more easily regulate. Like one of the big problems with these new energy sources, sort of renewables like solar and wind, is that you don't really control the generation, right? So I mean, the solar, you get a cloud, or the wind, you get a wind gust, or you get a storm, and then you're getting more power, and you cannot say, well, I don't want so much power now. But I want it later, and then later there is no wind, right? Whereas in the traditional generation, sort of like the hydro or the gas power plants or the coal plants, you have some control on when you generate. Now, depending on the source, your control may not be fast enough, right? So if you've got like a coal plant, well, you cannot like instantaneously change how much energy you generate. But you've got a gas-fired plant, you've got more ability to regulate that, and hydro actually turns out to be one of the fastest from my understanding, where you can really kind of, but of course, in order to do that, you have to have a good integrated sort of closed-loop system, going back to the reaction time that you were talking about. How do you know? You have to close the loop, that you were referring to the same thing. Like, if you don't know what the current demand is, and you don't have a way to measure that and to transmit that to the source, and to have some kind of global plan and a scale that says, okay, we need to notch it down, and you're going to go down this, you're going to go down that, right? If you don't have that integrated information system, you cannot take advantage of those resources that could be fastly used to adapt. So in an ideal world, you could say, hey, we have enough wind, we have enough solar, let's not generate so much hydro, right? So stop the hydro generation, or notch it down so we can balance the grid. And now when the solar is down, when the wind is down, then we can notch up the hydro, right? Or even you can use the hydro as a storage mechanism. You could even pump water up, right, if you had to. So you could use the few resources that you have that are naturally able to store energy and are fast reacting to kind of balance the whole grid. But in order to do that, you have to have essentially the software and the technology and the protocols and the data models and all these things kind of laid out. So we've been certainly looking at different standards that are there, and what are the technical solutions to provide that integrated sort of information distribution in real time and get that information going. And one of the things that we've been looking at is the OpenFMBA standard, partly because the OpenFMBA standard is kind of driven by some of those utilities, like Duke Energy has been very engaged with that, and also because they've kind of designed this standard as a kind of layered approach where different components can be kind of plugged in different ways, and it specifically kind of, they also use a publish-subscribe kind of model like you were referring in GridUp, but this publish-subscribe model is pluggable, so you can use different implementations of publish-subscribe. And because of our background working with the OMG and building the data distribution service being a very broadly adopted publish-subscribe standard, we've been involved with the OpenFMBs, supplying that kind of implementation of a publish-subscribe for that bus, so therefore our interest in there. So that's how we got in there. And then with the microgrid, we saw an opportunity to collaborate with these different players, both the utilities as well as the providers of the different components and the technical companies, on trying to essentially create proof of concepts that see all how these issues can play out. So this testbed, which is organized by the IIC, the main players, kind of like the key people that led the testbed was ourselves. We are at Real-Time Innovation at PI, so we're bringing there sort of our expertise in publish subscribe, kind of technology, data distribution. There is Wipro, which is sort of a utility type of integrator type company, and then you've got Cisco, which is providing a lot of the IT infrastructure. And then we've got collaborations with utilities like Duke Energy, CPS, and then we've got National Instruments and others that are also participating because of their interest sort of in providing components to the grid, as well as some networking technology like time-sensitive networks that are being seen as one of the technical solutions to some of the problems of synchronizing some of these networks. So what we're trying to do is basically sort of create a proof of concepts and put together everybody in the same kind of application with concrete use cases, concrete hardware, concrete software, to have it all demonstrated so that we can actually learn from that experience and we can demonstrate to other people. So it's both a technical goal as well as sort of a business marketing goal, because we want to be able to show it to people and have discussions and so forth. So in a way, some of these utilities, there was a question before about how long is it going to take. I mean, what we've seen is some of these utilities are very forward thinking and they want to get going immediately. Some of these other utilities are out there kind of seeing what we'll do it when we are told to do it, but we're not going to do anything proactively, right? And another way to look at it is, can we sort of give more, amplify the effort that those forward-thinking utilities are having and are making to make it more likely that other people will kind of jump on, or that the regulatory agencies will say, hey, we see the benefits, we're going to tell people to do this because we can see the economic benefits that to the country that we can get from this. So we've broken the thing in several phases. What we're trying to accomplish in one of the phases of the demonstration. We're kind of like the phase 2A, well, after we went through the designs and the different things, was getting to some practical demonstrations, was to kind of show how some of these harder problems of synchronization of the power quality analysis and the phase measurement units, how these type of units can be synchronized in real time. Some of the problem is that when you've got power going on in your grid, then you can just kind of use the grid frequency to synchronize the different components, but the moment you become islanded, you don't have this kind of master global synchronization. So things become out of sync and can become stable. So these kind of technologies are coming out with time-sensitive networks and network precise, like IEEE, time-sensitive kind of high-precision time synchronization can allow you to essentially get your components synchronized in a local area network, even if you don't have a global sort of external access to this single signal.
Out of curiosity, what are you down to in terms of minimal time length? Are you down to milliseconds? Are you down to hundreds of milliseconds?
So I think you need, sorry? I'll repeat the question. What's the kind of time synchronization resolution? I think the requirements are sub-millisecond for this type of systems. I think the TSN can do microsecond type resolution. Of course, TSN is kind of like a network level kind of technology, and then you've got all your layers of software that go above and beyond, like the operating system, the public subscribe infrastructure. So when it comes down to it, I think you're going to get sub-millisecond type of resolution.
Thank you.
I mean, right now, for example, for DDS, which is the public subscribe technology I was describing, typical sort of one-way latencies in a local area network tend to be around 50 to 100 microseconds. But they're not time synchronized, right? If you have the underlying technology to sync that up, then you can kind of preserve that sub-millisecond accuracy. So then, After that phase, we're going to have a phase where we'll do some field deployment. Another field deployment kind of has different aspects, so it has kind of a local aspect, but we're going to be looking at that TSN-based deployment with the different components at all times synchronized in a grid, microgrid, but then there is going to be kind of an integration to the cloud where there is like web service type technologies where people can essentially observe, schedule, do analytics on that type of system. So what have we done so far? So like I said earlier, we're kind of mixing events that are more technically oriented with other events that are more kind of trying to educate people on what we're doing and trying to get interest and collaboration. So we've already done a proof of concept based on TSN, so we know this technology is viable. We've essentially been working with the IIC. We did a couple of we've created a sort of an installation at National Instruments where we have like they've supplied the equipment there to kind of like the different components for a microgrid, so we can test things over there. They have a TSN network as well. We've published several industry pieces, and we've done a couple of demos, including a demo earlier this year at the National Instruments kind of user group that they have. They have a big workshop in their headquarters. Now, currently, we're sort of working back with the people at the OpenFMB that create the OpenFMB standard, and we're also basically working on a secure version of this to demonstrate, what happens when you inject security in these type of systems as well. So we're trying to essentially now move to kind of the next phase. So, so we're essentially creating another sort of piece of demonstration in our office in Sunnyvale, which is going to have a lot of the same components. It's going to enable our partners to be more agile because National Instruments is not officially part of this kind of IIC effort, so we kind of like gotten them like on a or sort of they've been agile helping, but they're not as engaged as we would like, so we want to be able to be a little bit more agile by creating the testbed and being able to control a little bit more what runs there. This is what the testbed looks like. So we're trying to illustrate both sort of that you can integrate the existing systems that are using a various protocol, like the MD3 or Modbus or 61850, which we're seeing as one of kind of the emerging protocols that are being adopted by a lot of people. So these all have to be integrated together. We're looking at also integrating sort of commercial software out there, like OSI SoftPi, which is sort of a historian type technology that's very prevalent in a lot of industries. So we're trying to see. So the angle that we're taking is how can we essentially take the best existing components and the best existing standards and kind of use them together to create a technical base upon which can be built applications on top. And I think the motivation a little bit what you were talking about when you were talking about the open source versus the open standards efforts and what are the economics of that, right? Because the problem is, it is a very complex software problem. And complex software is going to require a lot of investment, not just to develop it, but to maintain and take it forward. And how is that going to be paid for, right? So one approach, of course, there's multiple approaches. One approach is, well, you create the open standard, and then you create the open source, and somehow there's enough value on that platform that people are going to contribute to maintain that open source base. That happens with Linux and other things that people say, well, we want to see this in existence, so companies are going to just fund that because they don't want that thing to, they depend on it, therefore they want to improve the quality, so therefore funding. Another model would be, well, you create sort of the open standard, and then companies will come and you create the open source as a demonstration of that open standard, but then you think companies that are going to implement that open standard and offer sort of their services on maintaining the software, improving the software, and there will be an economic base on that. So that's another approach. And then the third approach is to say, well, we're going to try to leverage existing open standards and existing software bases that have their own ecosystem and their own business model behind them. And then if we can reuse those components and put them together in a way that makes sense for our application, then we don't have to really worry about financing that. Like if we use Linux, well, the Linux people will take care of opening Linux. If you build your own operating system, then you're going to have to worry about that, right? So to the extent that you can find things that fit already what you're trying to do, that have their own companies behind and open source behind, but their own ecosystem that finances the sort of the evolution and the maintenance of that, and you can kind of use that for your purpose, that is another way to solve that problem. So that's kind of like our thinking with the use of this, to kind of demonstrate that we can do that, and demonstrate that we can use ConnectCDS as one of those components, right? The publish subscribe technology that has its own ecosystem and its own set of companies, evolving that specification, have a business model behind that, and then, if it can be fit, then it's not part of the problem of the OpenFMB or this microgrid to actually figure out how that's solved, because that's already solved by somebody else. Of course, I'm biased on this because we're kind of part of this TDS ecosystem as the people that implement this, that define this specification and have a business model behind that. So we have commercial products that support this standard, right? So if you want to learn more about this testbed and where it's going and contact information and so forth, here you've got two names, one from our company, one from Wipro, that you can contact and get them more information. I have a second part of the presentation, which is like diving a little bit on DDS and why, kind of how it fits this use case, but I think this is a good kind of intermediate point if somebody has some questions about this specific effort. Yeah?
Yeah, my question is
Hold on
how
a second, we need a microphone. We're recording.
Thank you. My question is about the expected time period between now and when any product will be out in the market.
Well, that's so. I mean, that's really going to depend on how much demand is out there, right? So there is product. I mean, the building blocks are out there, but we're depending on the utilities to actually want to go forward and start deploying that. So I know that sort of people like Duke Energy, they've been very eager to start doing that, but they can't do this by themselves because they need the suppliers. So they've come up with this OpenFMB architecture, which use a lot of integrates, the MP3 and 61FX and so forth, but it requires things to be built with a certain data models and things like that, right? And they need, the Schneiders and the ABBs and all these other people that are building components to kind of adopt that and supply them because they are not a software company, right? So, how is that all get rolling? So that's the kind of Gordian knot that we don't have a solution, right? So, but we're kind of following what their lead is to some extent. Their thinking is like, well, this kind of needs to be demonstrated technically, so you know that the technical kind of risk has been moved out, and now it becomes a question of, are there going to be some leading energy utilities that are going to take this on and do it, or is it going to be some kind of regulatory process that is going to tell people that they need to do this, right? So I don't have an answer because I don't think this will end, but this doesn't mean that it will be used by anyone, right? So,
thank you.
okay.
Any other question at this point of the presentation? Or no? Okay.
Cool. So, this is.
There was just a second part on your slide.
Yeah, what is it? That's all the slides that were there? Okay. Let me get mine. But that's both because. Sorry about that. So, improvisation. Yeah, that's good. That's a good name. Real-time improvisation. So what's this Databus Technology I was referring to? So we're building this OpenFMB, as I mentioned, it supports multiple technologies underneath, and one of the technologies is DDS. DDS being a standard from the object management group. And what DDS was done is, DDS was built to kind of support this use case of integrating different technologies over a common database, right? So this slide is sort of taken from the IIC connectivity framework reference architecture, where basically they kind of came up to the conclusion that the only way to sort of integrate in an industrial type of context systems, legacy systems with future systems, was to kind of normalize the information into a common format, and then build kind of gateways and bridges that can take from the different formats into this common format. And of course, you've got to pick the right common format, and the right common format or common bus is going to be dependent sometimes on the kind of application domain that you are going to be using the system for. So, so as part of this study, the IIC created kind of their own analysis of what the different specifications are, where do they fit. They looked at some of the issues that you mentioned about interoperability, you know, what is interoperability and what layer of interoperability or aspect of interoperability is being addressed by each one of the different layers of the standards, and realized that there was a gap between the common set of standards that people are building their application on, which is the sort of transport level standard that provide connectivity at the level of getting my payloads from A to B and addressing, to the needs of the application, which are kind of at the level of semantic interoperability, like exchanging information, understanding the information. So in between, there is kind of something called, what they call the framework layer, which provides syntactic interoperability, which is the idea that you're going to be able to exchange information that has syntax kind of understanding, so the formats, data structures are understood, so you have a data model. You may not have a semantic associated with it because kind of that's at application level, so you may not necessarily know what the units are or how to interpret it, but at least you are getting sort of the right kind of richer set of information that you would get if you just connect at the level of a transport. So it's basically, if you combine something like a syntactic interoperability layer with something like a data model that comes from SIM or from 61850, then you get kind of that semantic interpretation of what this information means, because those specifications are defining that layer, right? So, so they basically layered that system and said we need, first of all, a transport that can get kind of the information around, that can deal with prioritization, timing synchronization, networks that can do the addressing, link and physical that can provide all these things. So the TSN type of technology fits down here, is giving you kind of the connectivity and the determinism. But you also need a layer above that provides kind of the syntactic level of integration. So it gets you the publish-subscribe information distribution, it gives you kind of a request-reply pattern, it gives you some kind of quality of service on the information, it can provide security, and so forth, right? And then on top of that, you're going to have sort of a semantic type of layer of integration, which is going to be something like the 61850 or the OpenFMB type integration or the grid app type of models that you're developing, right? So when they looked at this, they basically looked at what common, what this core databus would look like, what are good technologies to build your core databus on, depending on the application domain. So if you are in the cloud, maybe you need to build your common databus on RESTful web services, right? Because that's kind of what's adopted there. And if you look at what people are doing in the clouds for Amazon and so forth, everything gets kind of normalized into some kind of RESTful interface to things. Now, if you're in manufacturing, you may use something like OPC or OPC UA. And if you are in sort of more like dispersed autonomous type system, then you would look at something like DDS that was built for that type of application domain. And they have kind of in that study, I'm not going to spend time on that, they kind of give a set of criteria, trying to differentiate, you know, what are the non-functional characteristics of the different information exchange are and why you would pick one specification versus another for this common sort of database. So without getting into a lot of detail on this, what I want to basically say is, okay, so what are you getting with this common database? You're getting basically a simplification on the application that runs on top, right? Because a lot of these things that somebody has to address, like for example, addressing of things, discovering who's present, maintaining the presence, what's the state, you know, the publish, the subscribe, the request reply patterns, all the different things. Somebody has to take care of that. So if you've got a framework that provides those things, then your application can just build on top of that and doesn't have to implement those patterns. So, so there are some examples of these things. So you mentioned also the Grand Coulee Dam. So the Gamco recently kind of upgraded their control buses to run on top of DDS. So for the last couple of years, they've been running, they've upgraded their old equipment that was like 20 or 30 years old because they're trying to make it more agile, more integrated, be able to take those sort of energy demands and act on them. So one of the initial steps of doing that was updating their software. So they've built now all their software on the data distribution service, DDS, public subscribe framework. Now this is not related to the OpenFMP, so they haven't adopted a bigger framework. They've just gone into the first step of just modernizing, changing where the public subscribe capability that they have homegrown in there with a different technology. But it's not restricted, DDS itself is not restricted to this type of applications or energy type of applications. It's actually used in many other domains, right? So I have a couple of examples. This is an architecture from from a healthcare where they're actually doing hospital level integration of systems, and they are taking information, patient monitoring type information from devices attached to patients and integrating that to provide real-time information to the nursing rooms, to the doctors, so that essentially you can have continuous monitoring of patients as they move from room to room or from floor to floor in a hospital or even across hospitals, right? So you can see it's a very similar what was before the central domain of the power unit within the Grand Coulee Dam now can be seen as a main domain bus, but it's still this idea that you've got information, local information being exchanged between a set of applications in a local bus, and then that being integrated at a higher level, and then at a higher level, right? So that's you can almost think, well, that's also what the microgrid architecture ends up looking like, where you've got local information, and then you've got that information being integrated until you get to a national level type of integrated, or international, right? Because we've seen that. And autonomous vehicles is another example use case where now there is 3 or 4 of these new autonomous vehicles that are coming out, and multiple of those are now based on DDS. Again, because they want to focus on the planning algorithms, they want to focus on the sensor fusion algorithms, they don't want to focus on how to get public subscribe messages to be reliable. They figured we can use that. They can use that. So why, of all these different choices, why did they pick DDS? So they picked DDS because, first of all, it's a standard. So at the ONG, we've been working now for about 12 or 13 years on creating DDS standards. We started with the core DDS specification about public subscribe and data model and quality of service information model type of things. But then we've extended it to adding wire protocols, security layers, gateways to different specifications, a type system that allows you to take data types that are defined in one part of the system and then over time change them to a different data type. That is an evolution, but not break interoperability when the system is deployed. So solve a lot of problems that are practical out there and codify them into standards. And there is about 8 or 9 different companies now that have separate independent implementations of this standard. There's 3 of them that have open source implementations and 6 that have commercial implementations. Even we have some companies that are they have their own internal implementation of some public subscribe technology for their internal use within the company, and they've decided to migrate to comply with the standard because even they don't want to buy any software, they want the internal software to not be isolated in the world, but be able to, at some point, if they decided to migrate, they have the option to use something else, and they'll have to fund this internal development forever. And what this provides is basically a way in which information can be exchanged following this global data space shared data model, where applications are not directly describing, I want to send a message to you or I want to send a message to you. They really don't know who they send messages to. They just say, hey, there is this global information model that gets defined in terms of data types and topics, streams of information. And then applications simply just say, hey, I'm a source of this type of information, let me just post that to the database, right? And anybody in the system that subscribes to that will get notified, hey, there is a new value for this information. I'll just immediately get it sent to me, subject to the quality of service configuration. It could be reliable, it could be best efforts, it could be send me the last values, send me historical values. So those things are automatically handled by this kind of data distribution service information, data bus. And the applications themselves, they're just concerned about identifying what are the topics that they want and what is the quality of service with what that they want to use to read or write that data. Right? So it simplifies kind of what that, of course, DDS doesn't go out there and define what those data types are. So that would be something like, IIC or SIM or some other specification would go. DDS just says, well, if you want to have a data type, you're going to have to describe it to us into the DDS so that we know how to do a content filter on it and we can route it to the right place when you require data that is by content, right? Because you can have multiple sources of the information, right? They may all be publishing data on the same topic, like we're all publishing the state of the wind turbine, but there is thousands of wind turbines, and then there may be a display here that is saying, well, I only want to monitor this subset of wind turbines. So that would be kind of a content filter that says, wind turbines in this geographical area, or wind turbines with these IDs, or wind turbines that have this condition, like wind speed is greater than that, so you can have that flexibility when you are subscribing to information to select exactly what you want. Now, what's distinguishing from DDS to other systems, there's a lot of public subscribed technologies out there, right? So, there is NQP, there is NQVT, there is, a lot of things that have been created over the years. What's different about DDS is that it was built sort of for this kind of distributed peer-to-peer, more autonomous or agent-based systems, so more real-time. So it doesn't require having any centralized broker of the information. So when you do this using something like NQP and NQVT, your information model is quite similar. You also have the concept of topics and so forth, and you describe your data. But when I want to send information, I actually don't send it to you. I send it to some broker sitting somewhere, and then that broker says, oh, well, he wants it, and he wants and she wants it, so he forwards the information. But now the information gets funneled through a broker. Now, you could go and try to say, well, this is not really one broker, this is like a cloud, and it's got its replication, and it's got all these kinds of things, but this adds an intermediary, right? Can I scale or not? Question?
Yes. I'm hearing you saying you're putting it on the DDS, okay, on the bus basically. What's the limit of messages which can be distributed to the bus? Right now, it's not 3 per second. It's hundreds of thousands,
right.
Millions of thousands. I mean, in some sense, there's an upper limit.
Right. That's an excellent question. What's the limit? Okay, so that's really one of the main reasons to have a purely decentralized architecture versus a broker or server-based architecture. Because a server-based architecture, it forces all the data to be going through some place.
Right.
So you're going to be limited by how much bandwidth do I have to that server or that cloud? How much throughput that those services have, right? So you're going to have a limit based on that. In the case of DDS, information, this global data space is sort of a model of how you describe what you want and what you have. But when it comes down to how the information flows, the information is flowing directly from application to application. So all the knowledge of, oh, I want this and I want that, is propagated by the DDS bus to the different endpoints. So I, as an endpoint running DDS, have essentially local knowledge of who's consuming the information I produce, right? Because the bus is essentially saying, oh, I discovered somebody over there that also wants what you want. I discovered somebody. So I now have local view of who wants my information. So when I post an update to my information, it goes to everybody that has a subscription on it directly, right? So if I'm posting something to you and to him, it's just going from me to both of you. If he's posting something to those over there, it's going over there. So there is no relationship between this information flow and that information flow. So there is no intrinsic limit imposed by DDS itself on how much information can flow, because this could be completely different, there was completely different CPUs. Of course, in practice, there's going to be, for any one deployment, any one application is going to be limited on how much it can publish or consume based on its own network and CPU.
I was going to ask just a following question to that, but presumably there must be like a time message which gets put up onto the bus, the day of change, or the hour of change, or something like that, and that goes out to all the nodes, quote unquote, who are subscribing or interested in time? You know, we've got to be high percentage.
To all the
right?
nodes that are interested on that particular piece of information that you changed.
Yeah, but presumably a lot of them are interested in time, so that's essentially hitting the whole network, isn't it?
Not the whole network, it's hitting the consumers of that information.
But again, presumably most of the nodes are going to want to consume time information. They're
Oh,
gonna
you're saying is that time synchronization? Yeah, if you've got, I mean, DDS doesn't have any inherent things that have to go to all nodes, right?
Right.
But if you as an application developer or an integrator say, well, I want this time signal to be sent to everybody, then yeah, you're going to hit that periodicity at some level. So I don't have a question, and well, depends on how your network looks like, what kind of bandwidth you have. But I don't think you would design a system like that, right? Because you would essentially, you would send some kind of high-level time sync, and then you would rely on like local interpolation over that kind of global signal. You wouldn't want to send microsecond or millisecond updates of time, right?
I'm trying to
Right.
understand, you know, where's we constrained?
I mean, the constraint is that in the end, when it gets to it, applications have some information that needs to go to different places, and that's going to go through your infrastructure, so your routers. So DDS is not going to do a magic thing that is going to give you more bandwidth than you really have. But what DDS is going to do is it's not going to force you to have an artificial deployment, an overlay network that doesn't fit your physical network. So you're going to be limited by your physical infrastructure, not by some overlay thing that says, no, information is going to you, but it's not really going to you. It's first going over there, and then going over there, and then eventually will get to you. And now you're living with this other parallel overlay.
So, Gerardo, I'm curious, is there some sort of overhead penalty for having that local peer-to-peer capability?
Well, everything has some overhead, right? So I don't know how much overhead is beyond what an application would have to do itself. But I mean, when you write data, the data is serialized and kept in the local cache as long as you've configured your quality of service, right? So you could have configured quality of service of volatile. That means I write it, it gets sent to all the existing consumers, and then it's forgotten. Or if you could send it as a durable, that means I'm going to keep it because if a late joiner application comes, I want to be able to send that data to them. So then you're going to consume some resource. But if you had that use case, you would probably have to consume that resource. But it is more expensive than if you send it to the server, because the server could also do that for you, right? So you could say, well, I send it to the server keeps it. So now it's lighter weight in that. So it could be heavier weight if you're trying to do a more peer-to-peer and still keep some of these higher order qualities of service, like reliability of the information and so forth. So yeah, it's not an easy way to answer that question. But at the fundamental level, it's not really doing much more than essentially caching the information, keeping track of who's subscribed to it and sending it to that. So without getting into the details, that aspect of what happens to the information is controlled what in DDS is called quality of service. So quality of service is not just about timing, it's about how long is the information kept? Like, does it survive? Do I keep it for late joiners? Do I, when I send information to somebody, do I expect that other peer to acknowledge the information? And if it hasn't acknowledged, do I retry the same information? So some flows may require that, some flows may not require that. And those flows that require that have extra overhead, of course, to generate that extra acknowledgement traffic or heartbeating traffic. And because this thing in a broad system is complex and different flows have different requirements, DDS provides the capabilities to essentially at the fine level say this topic or this writer or this reader has this precise requirement. So it's not like an all or nothing type thing that everybody has to agree to. And then the protocol has been optimized to do those things, including being able to use multicast. So for example, if you have a multicast-enabled network, it will do multicast, which is something you couldn't do if you do MQTT or MQP because they're based. But is it going to do multicast if you don't have a multicast router? Well, it can do that, right? But it won't get in the way of taking advantage of those technologies if you have them there. And then when it comes down to the data, it gives you a language that you can use to define your data types. Right now, what OpenFMB has done, for example, they've taken the IIC 61850 and they've taken that into kind of UML models, and they've used kind of model-driven techniques to transform that into this representation. So they don't write these data types by hand. They've taken some existing model. They say, okay, well, these models are in the end structures that contain this, that contain that. We can generate this type of information, and then feed that information to the DBS system that can then write, marshallers and Marshall and so forth, which gives you then the ability to, publish and subscribe from C++, from Java, from C#, different machines, and so forth, and gives you that interoperability. So, the point being, it's broadly used across the IoT. So if you use a technology like this, then you're benefiting from the fact that somebody else has figured out how to fund their development and their support of this technology, right? There is an ecosystem of other applications out there using it. Companies out there have enough money generated from those applications to create it, and then you can kind of piggyback to that, like you would piggyback to Linux or to any of those other technologies that probably support it. Now, security is a big deal. It's part of DDS. Probably out of time, right? I just want to say that it was one of the driving forces behind the Grand Freedom and other things, because when they realized what the current system was and what people were trying to do with a lot of these protocols that were developed a long time ago, like DNP3, and they realized these things they're now being integrated into the broader grid and they're not secure, and how are you going to address that type of problem? And they studied, what kind of their threat model was and what kind of things they were concerned about and how would they solve their problem and what people were actually doing in their systems and putting kind of fake devices and all kinds of things. And so how do they protect that stuff? And they realized that DDS, which includes a security specification, was also a good fit for that. And why is DDS security a good fit for that? In kind of 2 minutes, is because DDS security is not trying to address security at the transport level. Like again, if you use something like MQTT or MQP, they think about security as a secure way to get from my device to the broker, right? So use TLS, whatever, and then everything is going through a single pipe, which means it has the same access control rules in that pipe. So if anybody breaks into the pipe, they break into it. DDS, on the other hand, is looking at the security at the data level. It's saying each topic, each writer, is responsible for its own security of that flow of information. If somebody is authorized, authenticated, and authorized to read that flow, it will get the cryptographic material it reads to just understand that one flow, not all the other things I publish to the bus, right? So because you are allowed to read these PNU values, you're not allowed to read this other thing or to write that other thing. So that, of course, people are going to find some way to break into the system. But the problem is going to be contained to whatever that breakage is. It's not going to give you like broad access. And all of a sudden you broke into the thing, you broke into the server, and you have access to the full information, right? So basically, as a conclusion, why the microgrid testbed and why DDS database in the microgrid testbed is basically to actually address these technical requirements that enable these more sophisticated sort of distributed energy resources and kind of partition the problem so we can leverage something that already exists and focus on building these higher value new domain applications.
Thank you, Gerardo. There's a lot of very rich information that comes out of all the people who've been doing so much work for such a long time on these standards and their applicability to various industry, including energy. So we have 18 minutes left until lunch, so I don't want to stand between you and lunch, but I think this is an opportunity to broaden or restart the discussion as you wish. So we've got a couple of questions, so we're going to go here and then you will be second. And
thank you. I have a couple of questions. One's for Ron and one for Pardo. Start with Ron first. Well, one of the use cases described is there are lots of users of energy. You mentioned like 1 million water heaters, and then there's going to be a use case where you bid for a certain amount of energy. You say you could bid for 5 cents a kilowatt hour or $1 a kilowatt hour, depending on your urgency to use it. So that becomes a trading system. Now, has it been considered that that these power walls, some examples that you gave, one could be charged to 25% or 10%, and at the same time one could be charged to 75 or 80%, and they could have an energy interchange without really getting to the utilities by having a local DC charging network. Is that a possibility that's been considered in this trading algorithm?
Yes. So basically your question is wandered into the notion of peer-to-peer interactions within the electric power system. There's quite a bit of debate about that. It's possible from a broad systems point of view with some limitations. So for example, if you're on phase A with your power wall, and I'm on phase B with my power wall, is there really any meaningful way for us to do a peer-to-peer interaction? Not without the third party involved. It's basically buffering the energy transfer since we're on different phases of the power system. So there's some fundamental electrical topology questions that have to be asked. On the economic side, it's certainly possible, but again, there's a transport component. So in the electric power system, in the existing bulk power markets, there's two steps involved, right? The first step is the participation in the day-ahead market or whatever market you're participating in which you bid in and you're selected as a resource to be dispatched at some point over the next 24 hours. Or you're a utility buying on maybe you have long-term contracts. So you get the contract to buy the energy. You also have to make a reservation in the transmission system for the transfer of the energy to you. So when you start looking at the delivery side, then you have to take into account the ability to actually operate the system. And in distribution systems, either the distribution utility or distribution system operator or network operator, whatever terminology applies in the part of the world you're in, has to come into play, and you have to take into account any constraints that would be violated or introduced by that transfer. So yeah, it's theoretically possible. Practically speaking, it's going to take a while.
This is where the problem with wheeling comes in, is that correct?
Wheeling is related.
Okay.
Wheeling is related.
Okay, so you're okay.
Wheeling is the ability to transfer power almost in the bulk power system from one chunk to another chunk, basically.
All right, thanks. Your second question was for Gerardo?
Oh, yeah, it was. I think you did mention, I mean, you've been referring to DDS and Databus and, the legacy protocols, GMP3 and Modbus. Now, as examples. Now, trying to understand this a little bit better in the sense that I imagine that these data streams through, whether it's GMP3 or Modbus, are going to be packaged, and there would be a DDS client sitting in each one of these embedded devices. Is that how it's designed to work?
Well, there's different ways. So how do you integrate these other protocols? Maybe legacy is kind of a perspective. Maybe to somebody says there is no legacy. This is going to take 200 more years, maybe. But there's a couple of ways, right? So I think there was an initial demonstration done where they had a DMP3 based system. They tried to distribute it over a wide area network. Of course, it's not secure, and they said, okay, both sides are speaking DMP3. Can I just tunnel this thing, right? And they demonstrated that using DDS by essentially taking the DMP3 packet, passing it through. I mean, that is not really what we're talking about here. That is when you could have used something else also. You could have like tunneling through some kind of SSL, SSH connection or something like this. I think what we're talking about here is that when you have multiple protocols, you cannot do n-squared conversions. It's just not scalable. Practically, you cannot maintain. So you're going to have to normalize into something. And to normalize into something, you kind of have to find something that is kind of maybe not perfect, but is good enough for everyone. It's like somebody says, what's the most spoken language in the world? Anybody? Yes, Chinese?
Yeah,
Okay, well, the claim I've heard is no, it's not Mandarin, it's not, it's bad English. Bad English. And why is bad English the most spoken language in the world? I mean, a good example of that, right? Is because you have to normalize, and English is easier to normalize than Chinese because it's more accessible. It has maybe whatever reason, right? So there are some languages that are better at bridging into. They may not be the best thing for any one thing, or maybe they are best for one thing, but as a normalization, you have to pick something, right? Because we can't all talk all languages, right? So we're going to have to agree on some common language. I think the same thing occurs here with this common infrastructure. So going back to your question about the MP3, so what would happen is you say, what is the MP3 trying to communicate? It's trying to communicate these data types, these flows. That has to be normalized into something equivalent in the databus. Now, what is that equivalent? That has to come up with from somebody that is in that domain that says, well, you know, my grid looks like this. These are the flows in my grid. Is OpenFMB, is GridUp, is, you know, some organization that says who defines what English is, right? Well, somebody defines that, and then people translate into that.
Yeah, just as a follow-up, that was kind of my understanding that it would go to layer 7 at some point, but I was thinking maybe you know, it would be a payload in an IP packet, and then from layer 3 it goes all the way to layer 7, and then that's where the normalization happens. Is that how it's constructed?
Normally, the normalization happens kind of like as a gateway type thing, like you've got the MP3 device and you maybe got a gateway, and this is typically industrial process manufacturing. They do that. They also have hundreds of buses, and they say, okay, we take that, that will be an adapter, and then we convert it into that. And that thing is the thing that needs to be agreed, like SIM. So you say, okay, well, it's going to be SIM. SIM defines the universal language for the grid, and now your problem is everything needs to be fed into some form of feed of SIM. So you have to agree on that SIM, which is a challenge by itself, right? Because there's probably other alternatives out there that people fight over. So that's a prerequisite. You have to agree on that. But you also have to agree on, now that you have SIM, how are you going to send that SIM around? Is that going to be your MQTT, MQP? Is it going to be a new protocol that gets created for the grid? Is it DDS? Like, you also have to agree to that. And once you have those things agreed, then you can convert from another protocol with another data model into this normalized bus.
Thank you.
Arne.
Yes, thank you. Very good. So my name is Arne Barre from Sintef, and in this case both Sintef Digital and Sintef Energy in Norway. And also from Europe, the Big Data Value Association and ERA, the European Energy Research Alliance. So from a European perspective, it's kind of interesting to see Synergies potentially. I know IIC has made an agreement with Industry 4.0 and also with the Industrial Data Space Community, or the International Data Space Association, where there are some other standards, I think, or emerging technologies related for both speakers. Related to DDS, there is an IIC standard now called NGSI, Next Generation Service Interface, coming out from FireWare and other activities that has some similarities or potential overlap with DDS. So I wondered if that has been looked into, given that there are some of these European collaborations now.
Right, I wasn't familiar with that standard, unlike you.
Yeah, that's something to look into, I guess, another somewhat related standard. And also the fact that it's not only using data for direct control purposes, but also for exchanging and sharing data among different stakeholders, where the industrial data space architecture is an architecture for data exchange and sharing and trusted control, which is relevant when there is a number of stakeholders that want to have access to data, but not open data for everyone. So that might also be something to look into. And related to that, if you go beyond just the smart grid itself, as it has been done before in Europe, we have the SGAN, which I guess has been, there is some historical work. Now there is some work on the next generation smart grid models, where one sees the need to include more information or other areas than in the current SIM. We have the need to go, say, into the homes, into the factories. And we have the concept of digital twins, which is broadening the scope by including other areas. And I wonder if this is an interesting area, since we are at the 1G meeting, for use of these ontology integration standards, because obviously will get beyond having one model for everything. We have a number of models that will be integrated and federated, and we have mappings between. And in 1G, it's always interesting to see if there are some potential areas of future standards that could be promoted by 1G. And I think this digital twin area, with a link to ontology federation, could be such an area. And I wonder if that has been thought about or discussed. Or if there are other efforts that goes in that direction.
So I'm familiar with some of the things you referenced, but certainly not the whole list. There's some other work in here also going on, largely driven by TNO in the Netherlands on FAN and FPI for DDR integration. And one of the things that we're trying to standardize that relates to their work and also work we're doing within the Department of Energy projects is the ability to have a standardized model of interfaces for distributed energy resources, both sort of a device-oriented standardization and then a services-oriented standardization. And the device-oriented standardization we're building around what you might call a battery equivalent model. So battery is sort of a universal distributed energy resource because it can be a source or a sink, and you can describe various characteristics of batteries, like state of charge, service life, ambient air temperature effects, all of these different parameters. You can take any other distributed energy resource and say, what are the equivalent set of parameters that describe the functional performance and behavior of that distributed energy resource so you can relate to it as if it were a part of a battery. So that's the standardization of the basic device interface. And then the question is, what are the services relative to grid operations, the energy services in other words, that could be provided by AER with those characteristics? So there's also the need to standardize the ability to describe those services in a way that not only reflects the services that we understand today, but the services we expect to emerge with a more decentralized grid with synthetic inertia and other things that we don't really know that much about today. So those are potential areas for collaboration, and perhaps right for the picking in terms of somebody like the object developer.
Yeah, and from your standpoint, well, I'm also not familiar with most of the things you mentioned, but I think I do know about the work of the Industry 4.0 with the IIC and the digital twin. I think that it's a good concept that needs to be evolved to a more distributed environment. Initially, the digital twin was created thinking about manufacturing use case, which tends to be, could be distributed, but it's kind of not very movable. And once you get to a more like distributed where the system is constantly evolving, you're adding components and moving components, the physical, the twin has to be more of a logical twin that doesn't try to say I've got a one device per one device. I think you need to kind of think at a higher level of abstraction. And I think what you're describing is kind of that kind of thing. It's like I don't really care about exactly what you are, but I can model you as a battery because you have, ability to generate energy, consume energy, and you have characteristics, and you need to have that kind of level of abstraction to be able to scale to larger systems and evolve them.
Yeah, the concept of system twin versus device twin or product twin.
Right.
So systems.
Right.
There's a particular problem with digital twins, and it's a general problem in modeling simulation of electric power system today, even without particularly talking about digital twins. So you can model phenomena, the physical phenomena of the power system up to a point. When you start talking about the transients associated with system protection and things like that, it's a whole different ballgame. And so depending on the time scale you're dealing with, you can have a fine digital twin, and then you get into those time scales where you can't, or at least can't with the technologies of today. So that's limitations in our ability to have the correct physical representation in models of those phenomena. And maybe we'll overcome that someday with enough horsepower on the computing side, but right now there's just some limits.
But very interesting discussion, which we could continue for quite a while, and actually you're encouraged, if you want to continue to network, to do that over lunch, whether you're in the official lunchroom or outside. I hear that the bar upstairs is where we solve all the OMG problems. And I witnessed some of that until the wee hours. Before, to follow up on what Arne is saying, there's going to be 2 European meetings, one of the IIC, one of the OMG in the first half of 2019. This will be excellent opportunity to bring European players to talk or to hear what's going on. So the IIC is meeting in Cork, Ireland in May.
In May?
In May.
Okay.
In Cork. I can find you the date. They're on the, you go to iiconsortium.org and you can find the list of events.
Okay.
So there's a meeting in Cork in May. It's 3.5 days, basically, from a Monday to midday on a Thursday. And there should be an additional day, which is sort of a public open meeting. I don't think the details have been firmed up on that. Secondly, the IIC will meet in Amsterdam. Sorry, the OMG will meet in Amsterdam. I think it's the week of June 24th or June 23rd.
The week before that.
The week before that, the week of June 17th then, or June 18th. Whatever that week is, third week in June, we're meeting in Amsterdam. So again, another opportunity to come. So if someone wants to come to the DDS special interest group, for instance, in Amsterdam, all they need to do is get in touch with Gerardo and get invited. For the IIC, you also need an invitation if you're not an IIC member, but then you also need to sign a non-disclosure agreement that basically acknowledges that everything you say in the meeting will become public knowledge among the IIC members, and so you're not going to reveal anything that you're not going to be able to claim confidentiality on that. So it's a little bit more complicated, but not that much. So take advantage of these things, and if others of you in the room have friends in Europe who want to learn about those things, tell them to come to one of those meetings to interact with our community. With that, it is exactly 12:30. I want to thank everyone for being here. I want to thank our fantastic speakers. Graham disappeared, but Ron and Pardo did a great job. Keep watching this space. Make sure you sign up the sign-up sheet. You will receive communication from OMG staff about the availability of the meeting materials. Thank you so much. Have a great rest of the day.